Hi everyone. For this video we're going to be taking a look at area formulas for three more polygons: parallelograms, triangles, and rhombuses. So let's jump right in and take a look at the area formula for a parallelogram. The theorem says the area of a parallelogram equals the product of a base and the height to that base. So most of the times you'll just see this written as A equals BH. And you'll notice that it's the exact same formula as we learned for rectangles. The formula looks exactly the same. There is one big difference, however. When we were looking at rectangles, both the base and the height were side lengths of the rectangles, right? So if we were looking at it, if we do a quick sketch of a rectangle right here, so a rectangle where the opposite sides are congruent and it has right angles all over the place. Maybe this was our base and that this side was our height. It's not going to be the case in a parallelogram. In a parallelogram, of course, it's kind of like a rectangle that's starting to fall over, is kind of the way I think of it sometimes. The base measurement will be a side length. So if I look at this, I might call this bottom side here a base, which would mean that the top side would also be the same, because those are going to be congruent, of course, because the opposite sides of every parallelogram are congruent. So those could be my base measurements. The height is, remember, the height can be thought of as the distance between two bases. So if we were measuring how far apart this base is from this base, we're not going to measure along this segment that's one of the sides of the parallelogram. Because remember, when we measure the distance between two objects in geometry, we measure along a segment that's perpendicular to the object. So the height of this would actually be this measurement right here. This segment that's perpendicular to the base, the length of that segment would be our height measurement for this parallelogram. And so if we were doing the area of this particular parallelogram, again, it's on grid lines, so we can just kind of count some boxes here. We would be doing base times height. So let's figure out what the base measurement is. And this can get a little bit tricky when some people have a hard time counting these boxes to try and figure out how long this segment is. They'll wonder, wait, do I count that box or not? Because it's only part of a box. And what about this one at the end? Do I count that or not? What I tell people is if you're faced with a picture like this and you have to count boxes to figure out this length, just start at one end of the segment and go along that segment counting how many boxes you cross over, how many full boxes. So if I start here and I start counting boxes as I move to the other end point of the segment, you'll notice I have 1, 2, 3, 4, 5, 6, 7. So this base is 7 units long. So we'll be taking a base measurement of 7 times a height of 1, 2, 3, 4. So the height is 4 units. So we'll be doing 7 times 4, which is 28 square units for this parallelogram right there. Not too complicated, right? One of the tricky things that might happen is you might be faced with a diagram like what I have in example 1. And the mistake a lot of people are going to make is they're just going to take the 18 and multiply it times the 11 and call that the area. But again, when we're doing parallelograms, we shouldn't be multiplying two side lengths together because that's not the way parallelograms are going to work. We need this measurement right here. So the 18 would be a base measurement, but then this right here is our height, and we don't know it. So I'm going to put an X right there. But what you might notice is that this triangle right here is a 45, 45, 90, right? If this is 45 and that's 90, that means that that must be 45 degrees right there. So this is a 45, 45, 90 right triangle where I know the hypotenuse is 11. So if I remember back from a couple chapters, I know that the side lengths of a 45, 45, 90 are related in this manner. The hypotenuse is equal to a leg times the square root of 2. So if I want to know what this x is, I can use this little formula. I can put an 11 where the hypotenuse measurement goes. I can put an x where the leg goes. And I have times square root 2. Now to get the x by itself, I'm just going to divide both sides by square root 2. And that'll leave me my x all alone. Probably need to grab a calculator and do 11 divided by square root 2, but it should give me about 7.8 when I round it off. So now I know this measurement is about a 7.8. So if I want to do the area of this parallelogram, I'm going to take 18 times 7.8, and that's going to give me, I think that gives me about 140.4 square units. If I wanted to be real proper and precise, I would put that unit on there. So this is a parallelogram with an area of 140.4 about square units. Next up, we got triangles. And the formula for the area of a triangle is, you guys might remember it. I'm sure you've learned it at one point in time. It looks like this. What does that stand for? It's the area of a triangle equals half the product of a base and the height to that base. So in other words, if this is my base measurement right here, call that B, the height is from that base. How far is it from that base to the opposite vertex? And of course, we always measure, remember, if we're measuring the distance between this point and this segment right here, we have to measure along a line that's perpendicular. So that's going to be my height. So you might want to jot yourself a note. The height will always be perpendicular to the base. And that'll show up a number of different ways. You just have to recognize that when you're doing area of triangles, the base and the height measurements are going to come from two segments that are perpendicular. The base will be one of the sides of the triangles, and the height is the perpendicular distance from the opposite vertex down to that base. Oftentimes that height will be given inside the triangle like this. If we were looking at a right triangle, so in other words, if we had a right triangle that maybe looks something like this, now this hypotenuse is going to look pretty ugly, but you get the idea. If we have this right triangle, then if this is the base, then this actual other side of the triangle would be the height. So in right triangles, the base and height will both be side lengths of the triangle. But in every other kind of triangle, only the base will be a side length, and the height will be given most of the time inside the triangle. The other weird case that you might have sometimes is if it's an obtuse triangle that looks something like this. And if this is my base, then the height measurement will actually be given, it'll kind of look like this. They'll give you this measurement outside the triangle as the height of that triangle. But in any case, once you know those two things, the base and the height, it's pretty easy. You just multiply them together and divide by 2. So if I was finding the area of this triangle, its base is 1, 2, 3, 4, 5, 6, 7, 8 units. So I'd be doing half of 8 times the height of 1, 2, 3, 4, 5. Half of 8 times 5, well 8 times 5 is 40. Half of 40 is going to be 20. So the area of this triangle right here would be 20. Let's take a look at example 2 here on your notes. I'm going to do example 2A, and then I'm going to leave example 2B for you to try. So to spare you the agony of watching me try and draw these triangles, I went ahead and used a computer program to put my triangles on there. You're going to have to do them yourselves, right? But we're looking at, in example A, a triangle that has sides of 10, 14, and 14. Well, that means it's an isosceles triangle, right? These two sides are congruent. They're both 14 units. And then this side down here is 10 units. Excuse me. If I need to know the area of this, I need to use that formula, half of base times height. Well, 10 can be my base, right? I can use that as my base measurement. But then these 14s, neither one of those is going to be the height. Because, like I said, the height should be perpendicular to the base. And these two segments are not going to be perpendicular to this base. The height down to this base would be along a line from this opposite vertex down along here, perpendicular to that base. Right? So the length of this segment right here that goes from this vertex of my isosceles triangle down to the base, and it's perpendicular, that is my height. Well, how am I going to figure that out? If I remember that when I draw that altitude from the vertex angle of an isosceles triangle down to the base, I remember that that splits that base into 2 equal parts. It bisects it. So if the whole thing is 10, then this part right here is 5. And now I have a right triangle where I know two of the sides. So I can use the Pythagorean theorem. I can set up a Pythagorean theorem problem that says h squared plus 5 squared equals 14 squared. So now h squared would be whatever 14 squared minus 5 squared is, which I believe is 171. And now h would be the square root of 171, which, let's see if I remember what, I'll do that on my calculator real quick. It'd be about 13.1. So now I can use this formula, and I can say half of 10 times 13.1, because I figured out that this height right here is 13.1. So half of 13.1 times 10 should give me an answer of about 65.5 for the area of this isosceles triangle. Now, letter B, you could do it similar to that. You could also use, if you remember when you're doing example B, this is an equilateral triangle, so all these sides are going to be 9. This angle right here will be 60 degrees. And that might be something that you'll want to use as you're doing example B. But right now, let's move ahead to theorem 11-4, where we look at the area of a rhombus. Now, a rhombus is, of course, a parallelogram. So you could use the parallelogram formula to find its area if you knew the base and the height of this parallelogram, or this rhombus. But there's also another formula that only works for rhombuses. It doesn't work for every kind of parallelogram. And it's that the area of a rhombus equals half the product of the diagonals. In other words, the area equals half of d1 times d2. d1 and d2 is just right. It's a way of denoting that these are two different measurements: diagonal 1's length times diagonal 2's length. So if we had this rhombus right here, and let's say we knew that this this segment right here was 6, and this segment right here, let's say, was 11. Excuse me. Then if I wanted to find the area of this rhombus, it would be half of 12, because if this part of this diagonal is 6, of course the diagonals of a rhombus are going to bisect each other. So if this part's 6, so is this part over here. So that entire diagonal would be 12. And then the other diagonal, by the same reasoning, would be 22 units long. So I would take 12 times 22 and then take half of that. So we'd be looking at half of 264, which is going to be 132. So with these measurements for these diagonals, that rhombus would have an area of 132 square units. So this last problem uses that idea, this formula right here, but it doesn't give you all of the information you need. It says we have a rhombus that has a perimeter of 44 and one diagonal that has a length of 18. Well, let's use this diagram to try and wrap our heads around what we're being told right here. So first of all, I'm going to get rid of some of these measurements here so I can write on this using the measurements that this is giving me. It says it has a perimeter of 44. Now, perimeter is all the sides added together, right? And there's 4 sides of a rhombus that are all the same. So if that perimeter is 44, then one side of that rhombus would be 44 divided by 4, which is 11. So I know that each of these sides would be 11. One of the diagonals has a length of 18. So let's use that as the longer diagonal in this picture. And if that's 18, that means that this part of it's 9 and this part of it's 9. Now, I know that the diagonals of a rhombus are going to be perpendicular. It's something I learned a few chapters ago, right? And if I'm going to use this formula, the d1, half of d1 times d2, I need to know this other diagonal's length. But what I notice is I have a bunch of right triangles where I know 2 of the sides. So if I want to know this side right here, if I want to know this segment, I can set up a Pythagorean theorem problem that says x squared plus 9 squared equals 11 squared. And now x squared would be 11 squared minus 9 squared, which is, let's see, 11 squared minus 9 squared is going to give me 40. So now x is the square root of 40, which we'll go ahead and turn into a decimal and call it about 6.3. So now if this is 6.3, then this entire diagonal, right, if this is d1, then d2 will be 6.3 times 2, because this part of it is 6.3 and this other part right here is 6.3. So d2 would be 12.6. So now the area of this rhombus that this problem is describing would be half of 18 times 12.6, and half of 18 times 12.6 is going to be about 113.4. All right, that's all the time I have for today, so I will see you next time.